Good morning, students. In the last class, we discussed up to parity bit. We discussed up to parity bit, and today the last topic in the unit 1, error detection and correction codes. Now, before moving into the topic, you are sending information from source to destination. You are transmitting information. Okay. Now, due to the noise in the transmitting channel or the environment, the information may corrupt or in the information will be changed. If the information change, that is known as error. If the change in the information occurs, that is known as error. Error means change in the information. If there is no change, we mention that it is error-free information. It is error-free information. Now, we know that, okay, from source, we try to transmit the data. From the source, we try to transmit the data, and to check whether the data is corrected or not, we add some check bits. This is for the check bit. Check bits are useful to identify that information is having error or error free. Check bits are useful to identify whether information has error or error free. Okay. This data plus check bits combinedly called code word. So from the source, we are transmitting the code words. Okay. Check bits, generally we use check bits parity. Parity bits as check bits. Generally we use parity bits as check bits. Okay. So from the source, we try to transmit the code words to the destination. Code word is combination of data and check bits. Code word is combination of data and check bits. Okay. Now, first we'll go with the error detection. Now, from source, we are transmitting code words. we are transmitting code words. Code word indicates combination of data bits and check bits. Okay. Code words we are transmitting not single code word we transmit set of code words. Set of code words may be C1, C2, C3 like this. Okay. We are transmitting these code words from source to destination. Now, the important point you need to remember is to detect error, the distance between any two code words in the set should be 2. To detect error, the distance between any two code words in the set should be 2. Remember this point. Okay. To identify the error is occurred, the distance between any two code words should be 2. Okay. Explaining this point. For example, you are transmitting some data. Okay. The code words are like this: 0, 1, 0, 0, 1, 1. Okay, like this. We are having two code words. One is C1 and the one is C2. What is the distance between C1 and C2? Distance between C1 comma C2. I told you distance between C1 and C2 nothing but the number of bits differ. The number of bits differ between C1 and C2. Here, how many bits are differ between C1 and C2? Anyone? Any bits differ ఉన్నాయమ్మా C1 C2 మధ్యలో?
1.
Yeah, only one bit is differ. Only one bit is differ. Okay, see 0 0 matching, 1 1 matching, but 0 1. So the distance between these two code words is 1. Now, from source you are transmitting the data to the destination. Transmitting the data to the destination. Now, there is a, while transmitting C1, there is a error occur on the third bit. This is the third bit. Error occur in the third bit and it is changed to the 1. Error occurred on the third bit and it is changed to the 1. So at the destination, what is the bit we received? 0 1 1. What is the bit information we received? 0 1 1. Now, can you tell me, is error occurred or not? We can't say error is occurred. Why? Because in the source we are having two code words 0 1 0, 0 1 1. If you receive any one of these two, the information is correct. You are receiving 0 1 1. So you need to consider there is no error. There is no error? Because we are unable to identify the error if the distance between two code words is 1. Here distance is 1. That's why we are unable to identify the error. Okay, Nama? That's why to detect error, the distance between any two code words in the set should be 2. Here, what is the distance between two code words? 1. That's why we are unable to identify. For example, if it is 2, the point clear, Amma? Okay. Okay. Why it should be 2 means if it is 1, we can't detect the error. We can't detect the error. If it is 1, we will, if it is a single bit error, we receive a data which is in the source set. If you receive the data, whatever the present in the source set, if you receive at the destination, you consider as error free. Okay. If you see a new set which is not present in the source, then you consider it as a error. Okay, Amma? When you say a error is occurred, if you see new code word in the destination, if you see new code word in the destination, then you can consider it is error. But it is not a new code word, it is already existed in the source, so there is no error. Okay. Now, for example, if we have distance 2, okay, now distance is 2, okay, 1 0, this is differing, 1 1 same, 0 1 differing. So the distance between C1 and C2 is 2. Now consider a single bit error has occurred. Okay, take anything C1 or C2, whatever it may be. In the C1, I am considering a error is occurred 0 1 0. While transmitting, this last bit is changed to 1. It is changed to the 1. So you will see 0 1 1. 0 1 1 is a new code word. Okay. Okay. While you are transmitting 0 1 0 1 1 1 1, you have to get either 0 1 0 or 1 1 1. Then we consider it is a error free. But 0 1 1 is not present in the source set. So it is having error. We can detect the error. So to detect the error, the distance between C1 and C2 should be 2. Okay. This is about the explanation about the point. Now, generally used technique for the error detection is parity code or parity bit code. Okay. Error detection code generally we use parity bit code for the error detection. Okay. And okay, Amma. Now take some data you are transmitting. Okay. 3-bit binary word you are transmitting. Okay. With 3 bits, how many combinations will get? 0, 0, 0, 0, 1, 0, 0, 1. Okay, Amma. This is the message. Okay. Message is like this: 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0. Okay, Amma. This is the message you want to transmit. Okay, this is data. Okay. For simplifying, we are dividing it into 3 bits. Okay. Now, this data is 3-bit binary word we are choosing. This data should be combined with check bits to transmit. Okay. The check bit we are using is parity bit. Check bit you are using is parity bit. Okay. This is parity bit is nothing but check bit, because from source you are transmitting the combination of data and check bits. Okay. So in the check bits we are using parity bit. In the parity bit also we are having two kinds. What are those, Amma? Even parity, odd parity. Okay. Now generate, we are considering this parity bit is even. You can consider anything, even or odd, but I am considering even bit. Now generate even parity bit. When the even parity bit will become 1, if the number of ones in the data is number of ones in data is odd. If the number of ones in the data is odd, the even parity bit will become 1. Even parity bit is equal to 1. Like that, write down equal to 1. Okay. Now I am writing number of ones in the data is 0. 0 means even. For the even, it is 0. Number of ones odd. So 1. This is odd. 1. Number of ones even. 1, 1, 2. So if it is even, 0. Odd, 1. Even, 0. Even, 0. Odd, 1. Okay. This is our C1, C2, C3, code word. Code word 1, code word 2, code word 4. Like this, C5, C6, C7, C8. We try to transmit these code words from source to destination. Source to destination. Now, at the destination, what we will do? Okay. Now, take data, add with check bits, here in our case even parity, and we are transmitting. Okay. This is at source. Taking the data, adding with check bit, and we are considering the check bit is even parity, and we are transmitting. Now, each code word is having even parity. So, observe here once. Observe all the code words. In all code words, number of ones is even. Observe. In all code words, number of ones equal to even. Did you observe? So whenever you are using even parity, the number of ones in the code word is even. The number of ones in the code word is even. Okay. So you are transmitting the data, and here receiving data, and in the receiving data we check number of ones wait okay check number of ones even, because we are using even parity. If you check number of ones even, if it is yes, accept received data. No, reject. Reject means the data is having the error, or information is having the error. Reject, because code word have error. Okay, when in the transmitting code word you are having number of ones even. Check any code word C1, C2, C3, whatever it may be. Take anything. The number of ones is even. For example, in C8, 1, 1, 1, 1. Total number of 4. Here, number of ones 2. Here 2. Here 2. Here 2. Here 2. Here 2. Here 0. So completely what it indicates, number of ones is even. So our work is easy to check the data is having error or not, the code word is having error or not. Okay, if the number of ones is even, then we will accept the data. If the number of ones is odd, then we reject the data because it is having error. Okay, Amma? In this way, we will detect the error. Do you have any doubt? Ask me. No?
Addition of parity bit should be done at the last, or can we do it at the first also, sir?
We can do at our convenient amount. We can do in the middle also. No problem.
Okay, sir.
We can do it anywhere. So, now drawback. See, take one code word 0, 0, 1, 1. Now, if there is a single bit error, single bit error. Means one bit is changed. Consider 0, 1, 1, 1. Now here number of ones is even. Here number of ones odd. Number of ones odd. So if the number of ones odd, what it will do? It will reject the data. So it is having the error. But if we have one more bit error, consider 2-bit error. 2-bit error. Okay, single bit error means we corrected this. There is one more bit error also there. Consider. So 1, 1. 1, 1. If there is a 2-bit error. So how many number of ones? 4. That is even. So it will accept the received data. It will accept the received data. So the drawback in this parity bit is we can detect only odd number of bit errors. Odd number of bit error means if there is a 1-bit error, 3-bit error, 5-bit error, like this, we can detect. But we can't detect 2-bit error, 4-bit error, 8-bit, 6-bit, 8-bit, like that. So drawback is we can't detect even bit error. Even bit means even bits 2, 4, 6, 8. Even bits error. We can't detect even bits error using parity bit code error detection. Okay. Here, okay. This is the error detection one with parity bit code. So what you have to do? Whatever the data given to you, you have to add check bit to the data, then it will be converted to the code word. Now code word you have to transmit, and at the receiving end it will check number of bits is even or not. If it is yes, it accepts the data, no, reject the data. And the drawback is we discussed here, if the number, if there is a 2-bit error, 2-bit means even bits error, we can't detect the even bits error. Okay, it will accept the data. If there is a more, if there is a 2-bit change or 4 bits change, we can't detect the data. We can't detect the error. Okay, next. That is error detection. And next one, error correction code. Error correction code generally Hamming code we use. Hamming code. We use Hamming code. Now, error detection and error correction are different. Error detection, error correction are different. Why? If we detect the error, that is okay, na? No. Error detection means we got a new code word which is not present in source. Okay, in the source we have the code words. So error detection means if we got a new code word which is not present in the source, the error detection is over. We can say that error is occurred. But error correction is not like that. Error correction means we need to find which code word we need to find from which code word error. Okay, we need to find from which code word the error happened, and we need to know error location. Error location. We need to find the first code word, then error location. For example, take the source okay 0001111. These are the two code words. Okay, you are transmitting. When you are transmitting and in one code word we got the error, in the 000 we got the error, so it is changed to 1. So 001 happened. 001 happened. So we will compare the code words present in the destination with the code words present in the source. In the source we have 0001111, but in the destination 001. This is a new code word. New code word. So this new code word we need to identify from which the error has occurred, either from C1 or C2. In the error detection, this is the new code word, so error occurred. That's all. But in the error correction, what we have to do is we need to identify from which code word the error happened. Here, the error happened in the C1. Error happened in the code word C1. Again, we need to identify the location. The location, this is the first bit, second bit, third bit. So error location is third bit. Error location, third bit. So in the error correction, what we have to find out is from which code word the error occurred and at which location the error occurred. Error location and the code word. We need to find both. Okay. And here in the Hamming code, error correction code means Hamming code. Now we know that to detect the error, the distance between any two code words should be 2. Similarly, for single bit error correction, the distance between any two code words in the source should be 3. Okay, Amma? For single bit error correction, the distance should be 3. For the error detection, it is 2. For the error correction, it is 3. Okay. So, we can generalize this one. For 1 bit error correction, what is the distance should be 3. Okay. So, this one you can write as, okay. Similarly, for 2-bit error correction, the distance should be 5. If you generalize for n-bit error correction or r-bit error correction, the distance should be 2r plus 1. This is the formula you need to remember. Okay. To do the error correction, the distance should be 2r plus 1. The distance should be 2r plus 1. Now, we'll discuss the basic principle of Hamming code. Basic principle of Hamming code or Hamming code generation. Okay. Now, okay. In the Hamming code, first, it is used to generate code words with the distance 3. Hamming code is used to generate code words with the distance 3. Take any two code words which are generated by the Hamming code, the distance will be 3. We are discussing with only single bit error correction. We are discussing only about single bit error correction. Our syllabus is limited to single bit error correction. Our syllabus is limited to single bit error correction. So we are discussing about single bit error correction. And each code word has m data bits and k check bits. Check bits means parity bits. So each code word is equal to m data bits and k check bits. So totally m k bits present. Code word is equal to m k bits length. Code word length is m k bits. Third point. And each code word location, okay, in each code word location of bits given with one to m plus k starting from MSB. So these are the m plus k bits. Okay, this is the first bit location, second bit, third bit, fourth bit, like this. So this is the MSB. We'll start with location. This is code word. Code word, the locations, how to write. This is the first location. MSB1 is the first location, second location, third location. So we are having m plus k bits. So the locations are m plus k. 1 to m plus k. You have to start writing from MSB. Okay. Each box is a bit location. Each box is a bit location. Okay, ma? Hamming code used to generate code words with a distance of 3. Each code word has m data bits, k check bits. So total length is m plus k. And for this m plus k bits, how to find the location? Location you have to start from the right side. Okay, you have to start from the MSB. You have to start with the MSB, most significant bit. Okay, and starting from 1, 2, 3, like this, you have to give the numbering. And last and important point, okay, next point, give the numbers. Fourth one. Now, k should satisfy equation 2 to the power of k greater than or equal to m plus k plus 1, or m should be less than or equal to 2 to the power of k minus k minus 1. Okay, k should satisfy the equation 2 to the power of k. Okay, and take minimum value satisfying the equation. Take minimum k value satisfying the equation. Okay, I am explaining this one. For example, data bits 4. Data bits 4. M is equal to 4. Find how many check bits needed. Find how many check bits needed. Find the k. To find out the k, you have to use this equation. Okay, 4 should be less than or equal to 2 to the power of k minus 1. Okay, Okay, whichever the value satisfying this equation, we have to go with those many check bits. We have to go with those many check bits. For example, here, if you take k is equal to 3, what will happen? 4 is less than or equal to 2 to the power of 3 minus 3 minus 1. 2 to the power of 3 means 8, 8 minus 4, 4. So, it is, for k is equal to 3, it is satisfying equation. Similarly, okay, similarly, this equation is also satisfied for the 4 also. This equation also satisfied for the 4 also. K is equal to 3, equation satisfying. Now find, let us check for k is equal to 4. K is equal to 4, what you will get? 4 is less than or equal to 2 to the power of 4 minus 4 minus 1. 16 minus 4. So 4 is less than or equal to 16 minus 5, 11. It is also satisfied. So this equation is satisfying for k is equal to 3, k is equal to 4. Which one to choose? Take minimum k value. Take minimum k value. So minimum k value is 3. So you have to take k is equal to 3. For example, if you take k is equal to 2, what will happen? 4 should be less than or equal to 2 square minus 2 minus 1. It is not satisfying. So whenever they will give data bits, we need to find how many check bits are needed. For that, you have to use this equation. M should be less than or equal to 2 to the power of k minus 1. Okay. You go with starting with 1, k is equal to 1, satisfying or not. Then go to 2, 3, 4. Okay. Here k is equal to 2, not satisfying. 3 is satisfying, 4 is satisfying. Then which one is considered? Consider the minimum one. So k is 3. K is equal to 3. Now, this is about the 4 points. Next, fifth point is, we will add check bits we do not add check bits at the end of data. We do not add check bits at the end of the data. We add check bit means parity bits. Okay, parity bits. We add parity bits at locations at locations 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, so on. Integer power of 2. Okay. Okay. We will add the parity bits at locations 2 to the power of 0, 2 to the power of 2, 2 to the power of 3, so on. 2 to the power of 0, 1, 2, 3, nothing but at 1, second location, third location, sorry, at fourth location, eighth location, like this. We'll add. Okay. See, Amma, ikkada first location, we add one parity bit here. Second location, we will also add parity bit here. Third location, we do not add any parity bit. Fourth location, we add like this. Fourth location, we add the parity bit like this. We do not add. This is the data, and generally we add to the check bits at the end. But in the Hamming code, we do not add the check bits at the end. We add at the respective positions to the power of 0, 1, 2, 3. And last point for the generation. Okay. Parity check bits, computed with process, with one process, that is, okay, the parity bit which is presented at first position we consider P1, this is P2, this is P3, P4, like this we will consider. Okay. Now P1, how to generate P1 or compute the P1? For this one, take one bit, okay, just to remember this bit, skip one bit. This is we use, take one bit, skip one bit, okay. I do not explain right now. While doing one example, I will explain. There you will understand better. P2, take 2 bits, skip 2 bits. P3, take 3 bits, skip 3 bits. P4, like this, whatever it may be, take 4 bits, skip 4 bits. This is what process to generate parity bits. Okay, Amma? This is the Hamming code generation process. Okay, how we will generate Hamming code for the data, given data. Okay, these are the points you need to remember. Try to remember these points. In the next hour, in the next class, within 10 to 15 minutes, we will complete the example problem. Then we will move to the second unit. Okay. In today's class, we discussed about error detection and error correction. For the error detection, we use parity bits coding. For the error correction, we use Hamming code. Okay, these are the rules. ఒకసారి ఈ రూల్స్ అన్ని మీరు నేర్చుకోండి. ఈ 6 రూల్స్ నేర్చుకోవాలి. నేర్చుకున్న తర్వాత విల్ go with one example problem in the next class. Okay, amma, ఏమైనా డౌట్ ఉంటే అడగండి. Otherwise, ending the session.
Excuse me, sir.
చెప్పమ్మా.
What if the parity bits only gets what do you say? Corrupted.
Parity bit corrupted. It can be akarama, it can corrupted. Parity bit also can be corrected.
How does the error get detected?
Yeah, that is we will see in the Hamming code. In the Hamming code, we will see that one in the next class. Okay, ma? Here we are having the positions now. First position, second position, third position like this. Okay, we are placing the parity bits also first location, second location, third location, fourth location. We are placing the parity bits at 2 to the power of 0, first location, second location P2, fourth location P3, like this. Now, at the error correction, we need to find out the location. Okay, first location, second location, third location, fourth location. See, in the place of location, we have the parity bits also. So the parity bits may also get corrected. So we will see how to do in the next class. Okay, ma, parity bits may also corrected, and we can rectify that. We can also rectify the error which is occurred in the parity bits. But simply first remember these 6 points. In the next class, it will be easy. With one example, your doubts will be clear. Okay, ma? Right. Anything? Okay.
Sir, did you check our marks?
చెక్ చేస్తానమ్మా, అందరిది కామన్ గా ఒకసారి ఫ్యాకల్టీ అందరితో డిస్కస్ చేస్తాను. అంటే ఒకరికి కాదు కదా మా ప్రాబ్లం, నేను మొత్తం రెస్పాన్సెస్ అన్ని పంపించాను కదా ఓవరాల్.
Yes, sir.
నేను అది ఓవరాల్ కాబట్టి అందరూ ఫ్యాకల్టీ ఒకసారి కూర్చొని మాట్లాడాలి. ఏం మార్క్స్ ఎక్కడికి వెళ్ళవమ్మా, ఏమన్నా కరెక్షన్స్ ఉంటే అందరికీ యాడ్ అవుతాయి. ఏమన్నా ఇక్కడ
Yes, sir.
ఏమన్నా మార్క్ యాడ్ అయ్యేది ఉంటే అందరికీ యాడ్ అవుతాయి. ఒకరికి ఇద్దరికి కాకుండా అందరికీ యాడ్ అవుతాయి ఏమన్నా మిస్టేక్ ఉంటే. ఓకే, రైట్.